Hello and welcome to iitiansgateclasses once again. So, in last lecture we were covering minimum spanning tree, and we covered Kruskal algorithm in last lecture. In today's lecture, we will see Prim's algorithm. So that is also for this minimum spanning tree, but there is a bit difference between Prim's and Kruskal algorithm. Okay, so let's start with Prim's algorithm. With example, I will explain like. What is this algorithm? So let's construct a given graph. So a given graph GVE, where V are set of vertices, E are set of edges. Okay, and the graph is something like B, C, D. I think it's the previous graph only. Okay, so between D and E, we have an edge with weight 10. Between B and D, we have an edge with weight 30. Here is 40, and here it's 20. Here it's 60. Here it's 50, and there is also a node A which have 70. Okay. Now, what was Kruskal algorithm? We draw all the nodes first, okay, and we start from the minimum edge, which is 10, okay, and then the next minimum which was 20, then 30, and the next minimum was 40. Okay, but 40 will make the loop. See the loop. We can start from B and again come back to B. Okay, so it is a loop. So we cannot enter this edge between C to E. Okay, and then if we draw this node, this edge, this cannot be also drawn. Again, we have a loop. Similarly, we cannot draw the other one between B and E. It will also make a loop here. Okay, so we started from minimum to maximum edge. This is first minimum. Okay, let me give an order here. This is first edge. This is second edge. This is third edge. This is fourth edge. This is fifth. With increasing weight, okay? With increasing weight, I'm labeling them. This is sixth, and this is seventh edge. Now, if you see, once we enter the first one, second one, and third one, with increasing order of weight, we cannot enter fourth, fifth, and sixth because they are making cycle. Right now, I'm drawing Kruskal algorithm. This is not Prim's algorithm. Okay, this is Kruskal. After that, I know that, okay, once I have drawn this much, this is the last edge, okay, 70. Now, in Prim's algorithm, we start with the vertex and we cover all possible edges first, all possible edges that can be attached to that vertex, right? Then we move on to the next edge. Let me give you an example with this graph. It will be clear. So if you execute Prim's algorithm, it will go like this. First, you draw all the nodes B, C, D, E, and A. Okay. Then you pick one node. Pick one node. For example, if I pick E, okay. I randomly pick a node. I pick E. Okay. So what is the minimum edge which is on, what is the minimum edge on which one end is B, is E, okay? For example, here we have three edges which are attached to E. There are three edges, this one, and this one. So we have three edges actually, okay? Out of these three, this is the minimum one. This is the minimum one. 10 is the minimum one. Okay, now we have discovered two vertices. Instead of one, we have two vertices now, D and E. Now we will pick all the edges which are on D and E, and we will pick minimum out of those. Minimum out of those. Okay, so let me highlight those edges. Those edges. Okay, this one we have already selected. All the edges attached to D and E is this one is this one, Okay, this one. Another one is this one. Okay, this one. Another one is this one. And another one is this one. So these all are edges attached to D as well as E. These all are the edges attached to these two nodes. Because 10 we already selected, 10 we have already selected. Out of these highlighted edges, what is the minimum one? Which one is the minimum one? We will select this one. So this one is the minimum one, 31. Okay, so we say that, okay, 30. 30 is here. Got it? So now we have three nodes. We have already explored three nodes, B, D, and E. Out of B, D, and E, which one is the minimum one? Okay, which edge is minimum one? Okay, so I can draw it like this. From E, I am having these many edges. E, I have 50. One edge is 50. Another one is 40. Okay, these are not already explored. From B, I have one edge is 70, which is not already explored. One edge is 20. Another one is 50. Okay. And from D, we have a 60 only, which is not already explored. 160. Okay. From B, we have one more edge with 20. Okay. So out of all these edges, let me draw this very clearly with you for you. Now we have explored three nodes. Okay, so you need to consider all three nodes and all the edges which are all not already covered, which haven't already covered, and attached to B, D, and E. Let's see all those edges. So from B, we have 20, one edge. Okay, this edge 20, and 50, this edge, and one edge is 70. From E, we have 50, which we haven't explored yet, 40, this one. And from D, we have only 60, which we didn't cover already. Out of these edges, we will pick the minimum one. What is the minimum one? This one, 20. 20 is the minimum one. Okay, 20 is the minimum one. Out of all these edges, 20 is the minimum one. Okay, so what we do? We say that, okay, let's enter the 20 here. Then this is covered. Let's erase 20 from here. Let's erase 20 from here. Okay. Now we also have C right now. So we have to consider C also. So C have which edge? One is 20. 20 is already covered, right? C have 150 and 60. This CD is 60, right? CD is 60. And one edge is 40, which we didn't touch yet. So out of these, if we pick any of the edges, it will make loop here. It will again make loop. So we don't want to make loop because there is no loop in min heap there is no loop in minimum spanning tree. Okay. So we can't consider this edge or this edge or this edge. We can't consider those edges. So we eliminate this edge, this edge, this edge. Once we try to put these edges, it will make a loop. So we remove that edge. We try to put this edge, it will make a loop. So we have to remove it. We try to put this edge C and D, it will make a loop. Okay, so we remove it. Try to put this one and it will make a loop. So we can't consider this. So we only remain with one edge, 70, this 70. Now, if you remember that, the Kruskal algo was also giving the same, same answer. Once we have unique edge weights like this graph, we will have unique minimum spanning tree. Minimum spanning tree, unique. This will be unique if all the edge weights are unique. Remember this. Sometimes they may ask you in the exam that if we have a distinct edge weight at each edge, will there be more than one minimum spanning tree? No. The minimum spanning tree will be unique. Either whether we apply Prim's algorithm or we apply Kruskal algorithm, it doesn't really make a difference. Okay. So in Kruskal algorithm, we were starting with minimum edges, and we increase the edge weight. We consider the edge weight with like a higher edge weight. If we don't make a loop, insert it. If we make a loop, we don't consider that edge. Okay, in Prim's algorithm, we start with one vertex, okay, and we explore all the edges related to that vertex, all the edges related to that vertex, and we consider the minimum one. Like here, we started with E. So let's do one thing. Let's consider this example again, and we will start with B in that in this example. Okay, so let's draw this again. B, C, E, D, so we have 70 here, 20 here, 30 here, 10 here, and 40 here, 50 on this edge, and 60 on this edge. Okay, now let's try to make, let's start from B. Let's start from B. We draw B. Okay, and we say that first let me draw all the nodes. Because you know that in minimum spanning tree, all the nodes will be there. Okay. Now, if we start with B, what is the minimum edge which is attached to B? What is the minimum edge which is attached to B? Okay. This is the minimum edge which is attached to. This is not the minimum in the graph. This is minimum because we are starting from B. This is the minimum which is attached to B. At the one end of this edge, there is B. Okay, so we enter this B here. Now we have two nodes, B and C. We have two nodes, B and C. So we have to consider all the edges attached to B as well as C. Okay, so we will consider all the edges attached to B as well as C. Let's see that. Okay, so this is the one, this is the one, this is one more, and this is the one, and this is the one. Out of all these check marked edges, which is the minimum one? This is the minimum one, 30. Okay. So let's remove this check mark from here. Sorry. Okay. Now, D is also in the queue now. So we have explored three nodes, B, C, and D. Out of all the edges attached to B, C, and D, which one is the minimum one? So now out of all the edges attached to D, C, and D, let's mark those edges. This one. Okay, this one, and this one. So we are considering these edges because these are attached to D, C, and B. D, C, and B. Okay. So this one, 10 is the minimum one. 10 is the minimum one. Let's enter it here. Now, from B, C, D, E, which is the minimum edge? B, C, D, E, which is the minimum remaining edge, which is 40. So if you try to enter 40 here, it will cause an issue because it will make a loop, and in minimum spanning tree, we know that there is no loop. So we won't consider this edge. Okay. We won't consider this edge. So we cannot consider 40, we know that. Again, out of these marked and remaining edges, 60, 50, and 70 is the option. If you try to enter 50 here, 50 here, it will make a loop, right? So we can't consider this edge. If you try to enter this 60, it will make a loop, so you can't consider this edge. So which one is the last one? 70 is the last option. So you enter it here. This will make a minimum spanning tree. So the time complexity analysis we will do once we cover single source shortest path algorithm, which is Dijkstra algorithm, which is our next algorithm. Okay, so this is the minimum spanning tree. Minimum spanning tree of this graph. Okay, this is the minimum spanning tree. So Prim's algorithm works like this. It explores vertices, then it considers the edges attached to those vertices only. It won't consider the whole pool of vertices. The search space in which we need to consider the edges increase vertices by vertices. Okay, it won't increase something like you just consider all the edges initially, like Kruskal algorithm. So this is the basic difference. Okay, so there is one basic question already asked, that at any point in this in Prim's algorithm, okay, if you know that once we started with B, our graph, our minimum spanning tree goes like this. First we entered this 20, okay, initially it was like this. Then we consider this edge D, then we consider this edge E, okay, then we consider this edge 70. So at any stage or any pass of the algorithm, the tree remains connected. The tree remains connected. For example, we start something like this. In Prim's algorithm, the trees remains connected. Initially, we explored only B. So it's connected. There is a single node, it's connected. Then we explored this one, 20C, in the second pass. This is connected, right? There is no other node. We are not considering each and every node right now. We are considering the explored nodes. So once you explore a node, it's already a part of that spanning tree, that intermediate spanning tree. So the intermediate tree is connected here. It is not like B and C is here and E is here, right? No, it's not there right now. Once you explore it, you will add that node to the tree. Once you explore it, you will add that to the tree. So sometimes in examination, it has been asked that in which of the following algorithm, Prim's or Kruskal, at any point of the algorithm, the tree is connected. It's the Prim's algorithm, not Kruskal. Okay, so you grow the tree something like this. Once in the second pass, your tree look like this. In the third pass, your tree look like this, because you have started with B. Okay, 30 D. Then it will look like this, 10 and E. Then you add it here. Okay, so at any point, the tree is connected. Okay, so these are the questions that may be asked. So I am trying to cover some more notes here. These are very important because minimum spanning tree is a very common topic for each examination. So you need to understand that. Okay, note that for a given graph, more than one minimum spanning tree is possible. Minimum spanning tree is possible. But the cost of that minimum spanning tree, cost of all the minimum spanning tree. If we have multiple minimum spanning tree, sometimes we don't have multiple minimum spanning tree, sometimes we do have. I will cover that case also. Okay, sometimes we do have multiple minimum spanning tree. In case of multiple minimum spanning tree, cost of each minimum spanning tree is same. Okay, remember this, cost of each minimum spanning tree is same. The second important point is, if at all for the given graph more than one minimum spanning tree. Right now, I will denote the minimum spanning tree as MST. Okay, if I write MST, you should understand I am writing minimum spanning tree. Okay, if we have more than one minimum spanning tree, then in the given graph for which we are finding the minimum spanning tree, some edge weight must be repeated. There has to be some repetition in the edge weight. Okay, then only multiple minimum spanning tree are possible. Okay, what I'm trying to say is, if there are multiple minimum spanning tree for a graph, if there are multiple MSTs for a graph, okay, then there must be repetition of, sorry, it's not writing, repetition of edge weights. Okay, are you getting my point? So in a graph, edge weights will be repeated. So it is not necessary that if edge weights are repeated, there could be like a multiple minimum spanning tree. So let me give you an example. For example, if I have something like A, B, C, D. Okay. If I have edge weights like 10, 20, 30, and you can say 30 here, right? 10, 20, 30, 30. Now, if you try to identify the minimum spanning tree, we will have two minimum spanning trees. One is this one. Another one is this one. Okay. See here that edge weight are repeating. That's why we have two minimum spanning tree. But right now I will cover one more scenario where edge weight are repeating. Still we have only one minimum spanning tree possible. Okay, still we have only one minimum spanning tree possible. So if you have 10 here and C, D, and let me write E here. Like 20, 30, 40, and let me write 40 here. Now there will be only one minimum spanning tree. You cannot have multiple minimum spanning tree here. The minimum spanning tree will look like this: 10, 20, 30, and 40. Okay. Now, if you try to create one more minimum spanning tree out of this, it won't be possible. A spanning tree where the weights are less than this one. Okay, and the first note that I created, that if we have two minimum spanning tree or multiple minimum spanning tree, the cost of each spanning tree will be same. Like this. What is the cost here? It's 60, right? It's 60. The cost of this also will be 60. Okay, if we have multiple minimum spanning tree and cost of one is less than another one, then the second one won't be called minimum spanning tree, right? For example, if I have two minimum spanning tree and here the cost is 50, for example, then this will be minimum spanning tree and this won't be minimum spanning tree because its cost is greater. Minimum spanning tree is minimum because its cost is minimum, right? So here cost of both of these are 60. So these 2 points are very considerable and important. Now, let's see the next algorithm, or some more general statement which are basically asked sometime, because sometimes you face many theoretical questions on minimum spanning tree, and because it's more like a theoretical topic compared to the numerical, you find more theoretical question on this topic. Okay, so let's see that what it's saying. Okay, so I am writing some statement and you need to identify whether those statements are true or false. Okay, so the question says that I have a graph G, which is basically like a simple graph, okay, with n vertices or nodes, you can call it. There are n nodes in the graph, okay, and W is the minimum weight. W is the minimum weight, okay, minimum edge weight, you can say minimum edge weight. It is given that the small w is the minimum edge weight for all between all the edges. W is the minimum edge weight, okay, for an edge E. Okay, so for example, if we have a graph, something like very complicated graph, I'm just writing some graphs, okay. So for example, if this is the edge E, the AB edge I am denoting as E, and its edge weight is W, and this is the minimum in the whole graph. This is the minimum in the whole graph, okay. So there are some statements and you need to identify whether that statement is true or false. Okay, E should be in every MST of G. Should it always be true? It is true once all the edge weights are distinct. If all the edge weights are distinct, let's consider Kruskal algorithm here. We start with the minimum edge, okay? We start with the minimum edge. Okay, if all the edge weights are distinct, then this is true. Else it could be false, false. Let me give you an example. A, B, and C. Okay, so if I say that 10 here, 10 here, 10 here. Now that edge, I'm saying that, okay, this is the edge E. Will it be the part of the minimum spanning tree? Let me write a spanning tree where this is not the part. A, B, C, 10 and 10. See, here if we are making a cycle where there are two edges having minimum weight, okay, so one edge won't be the part of the minimum spanning tree. If we have a cycle in a graph where two edges having equal weight, which is the minimum, one of that minimum weight edge won't be the part of minimum spanning tree. Remember this. If two edges are a part of cycle and those edges having minimum weight, one won't be the part of minimum spanning tree. So this statement is true only if E should always be part of MST. This is true only if edges are distinct. Okay, else it will be false. And the second statement is, it says that every MST of G must contain an edge with weight W. So it's saying that edge need not to be the edge E. Okay, previously what we were saying that there is an edge with weight W, there is an edge E. We labeled that edge as E with weight W. Will that be part of minimum spanning tree? And we have seen a case where it was not the part of that minimum spanning tree. E is having minimum weight. Still, that is not the part of minimum spanning tree, where there is a cycle and we have multiple edges with minimum weight. Now, it's saying that every MST of G must contain edge with weight W. Now W is minimum weight. So if we start with Kruskal algorithm, because Kruskal and Prim's will give us same graph, or if not, equal weight graph, equal weight minimum spanning tree. Okay, not graph, minimum spanning tree. Then in that case, what will happen that there will be an edge which will have this W. If this is not true, that tree won't be minimum spanning tree. Okay, remember that. It need not to be that edge would be this E labeled edge. E labeled edge. But there will be a edge with minimum weight W. If a edge can have minimum weight W, if you have multiple edge, one of that edge will always be part of MST. Okay, you can try to draw this, and you won't be able to have a spanning tree where the minimum weight edge won't be there. If we have multiple minimum weight edges, one of that will always be part of a MST. Okay, that's what this statement says. So this is true, always true, always true. Another one is if this E is not in MST, not in AMST, what it indicates? What does it indicates? It indicates that there is a cycle in given graph, because minimum spanning tree can't have cycle. So there is a cycle in the given graph where this edge E with minimum weight W is part of that cycle. Okay, part of that cycle. So these are very important statements for our lecture now for minimum spanning tree. Let's move on to the next topic. If you don't understand, try to look up for more examples of minimum spanning tree. You will understand these statements. These all three statements are very important. Okay, for that you will understand the minimum spanning tree better. Okay, now let's move on to more graph representations. For example, we have a graph like A, B, C, and D. Okay, and we want to represent the graph. If graph is looking like this, okay, these are the edges. And what do we want to say that? We want to say that, okay, let's represent this graph. There is no edge weight right now, okay? But we want to represent this graph in some format so that computer or any person can understand it. So there is one representation which is called urgency matrix representation. Urgency matrix representation. Urgency matrix in this one, this is quite easy. We draw the matrix like this: A, B, C, D, A, B, C, and D. Okay. We write like this. And wherever there is an edge, there is no edge from A to A, we will say 0. We have an edge from A to B, we will write 1. Edge A to D, A to C, we write 1 and 1. From B to A, we have an edge. From B to B, we don't have an edge. From B to C, we have an edge. From B to D, there is no edge, 0. From C to B, A, D, all three, 1, 1, 0, 1. Okay, C to A, C to B, C to D, we have an edge. From D to we have A and C. So 1, 0, 1, 0. So this is how we can represent. If we say that, okay, we want to identify whether there is an edge between A and C, we'll say that, okay, A and C, we have an edge. Or there is an edge between C and A, C and A. If it's undirected graph, in undirected graph, we don't have this arrow-like structure, like arrow. Okay, if there is undirected graph, it means that in both the AB and BA, AB and BA, see, this is A, B, what is BA? BA, okay. This is AB and this is BA. In undirected graph, if we have an entry between AB, we will also have an entry for BA, okay, in undirected graph. For directed graph, for example, if we represent the directed graph like this, okay, like this, in that case, we won't have, right now, we are specifically saying that there's an edge between, there's an edge which is having direction AB. There's no edge for BA. So here we will write 0. Here we will write 0, okay. So this is how we can represent a graph using adjacency matrix. There's one more representation, which is called adjacency list. Adjacency list. Okay, let's consider a graph 1, 2, 3, 4. Okay, so let's try to write down the representation. What we will do, we will create a list with number 1, 2, 3, and 4. Okay, so this is an array or list. You can say array. Array with all the nodes. Okay, so this is array. So in array, for 1, we have a list pointer here, list pointer here. Once we cover data structure, we will understand how a list works. But for now, consider a list pointer here. There is a pointer which indicate to a list. One more list pointer here, one more list pointer here, one more list pointer here. Okay, for now, 1 have 1, 2, and 4. So we say that, okay, there is a node 2 here. There is a node 3 here. And there is a node 4 here. So if you want to check that how many edges this one have, you can check that, okay, one have 3 edges, 1 to 2, 1 to 3, and 1 to 4. Okay, from 2 we have 1 and 4. So you write it like 1 and 4. From 3 we have 1 and 4. 1 and 4. From 4 we have 1, 2, and 3. So there is 1, 2, and 3. So this is adjacency list method. Here you don't have to create a matrix of n by n. If you have n nodes, in the previous example, we have to create a matrix of 4 by 4. See, there are 16 entries, 1, 2, 3, 4, 5, 6. We have total 16 entries, right? You don't have to create 16 entries. You will create only 4 entries. And for example, if you have very sparse graph means we have some entries like 1, 2, 3, and 4. We have only 2 entries. Then this matrix will take too much space. It will take constant space of n by n, or you can say n square. Here it will take very few space. Like, okay, you write 1, 2, 3, 4. And here you represent 4, like against 1 you will write 4, and against 2 you will write 3, against 3 you will write 2, and against 4 you will write 1. So this is a very simple method here which you can use for adjacency. Okay, so now we have a problem which is called single source shortest path. Many times you have seen, and the application of this algorithm is mainly in networking. Okay, network, you have multiple nodes or routers, you can say router hubs, your computer devices. They are connected in some network, very complicated network. Okay. and we can represent that network as a directed graph. Okay, where this node can send some packets to this node can send some packets to this node and this node. So now if from this node you want to some packets to this node, what is the minimum path? For example, if this node is very old router, or you can say that this node is very far. Okay, in term of distance and load, this is very heavy load node. Here you represent that this will take 70 unit of time or some 70 cost. This cost can be represented as a representation of time or distance or any kind of loss also. So you can say that if I try to send a packet from this node to this node, there is a possibility, very high possibility, that my packet will lose. I won't be the end destination won't be receiving this packet. Okay. Similarly, you say that okay, now I can send it from this also. So this is 40. If I try to send it from here, this will take only 40, and here it will take 10. Here it will take some 20. Here it will take only 5 units. So I can send it from here to here, from this one to this one, and this one to this one. Okay, so it will take some 95 units of time, or 95 units. And if I try to send it from here, it will take how much? 40, 10, and 5. So it will take 50 units. And my problem is that I have given that this is our source. From this source, for each node, identify the minimum path. Not only this node, not only this node. For this node also identify the minimum path. For this node also, for this node also, identify the minimum path. So that is our problem. For a given node in a network like structure, a network structure we can represent in the directed graph format. I will take an example and I will tell you like how can we represent a network into a like graph by only drawing the graph. Okay, so you can consider that graph as a network, and you can say that the problem is I have a source. Source can be your computer or any server, which is trying to send some data or some signals to each and every node. How much time will it take to send that time or cost? What is the minimum cost to send the data from that source to every other node? So that is why it's called single source shortest path algorithm. Okay, let's try to draw a graph here. Graph is quite complicated because to understand this algorithm, the algorithm is Dijkstra. Okay, let me write the name here. D-I-J-K-S-T-R-A. Dijkstra's algo. Okay. First, let me try to write the graph here. Graph will look like this. A. We have B, C. Sorry. D here, C here, E here, F here. Okay, from A to B, we have an edge of 50. This is directed. So B can't send to A with 50. Only A can send to B with 50. Okay. From A to D, we can send with 2. From B to C, we have 2 edge weight. Okay, and we can directly send from A to C also with some edge weight of 25. Okay, then from B to D we can send with edge weight 8. Try to write in this order only because this graph is complicated, so you can lose the numbers also. For example, you may be confused that if 25 belongs to this edge or some other edge. From D to B, I can send with cost 3. Okay, cost 3. And from E to F, I can send it like with cost 2. From D to E, I can send with cost 4. From E to C, it will take 1 cost. From C to E, it will take 5 cost. From C to F, it will take cost 3. From D to F, it will take exactly 1. Okay. Now from D to C, there is also one possibility, which will take 1 only. Okay. Then B to E also, we have an edge from B to E, which will take 3. Okay. Now from A to E, we have an edge of with 3 weight. A to E, it is also 3. A to F, we have an option with 10. Okay. I think these are the only edges. Okay, 1, 2, 3. Sorry. From B to F also we have an option. From B to F, we have an option. We can send with cost 6. So F have 1, 2, 3, 4, 5. 5. 1, 2, 3, 4, 5. Okay, C 4 and D have only 1. B have 2. Okay, so this is the graph. Okay, let me try to repeat. From A to B, we have 50. A to D, we have 2. From D to B, we have 3. From B to D, we have 8. From B to C, we have 2. From B to F, we have 6. From E to F, we have 2. From E to C, we have 1. From C to E, we have 5. From B to E, we have 3. Okay, from B to F, we have 6. Okay, from D to F, we have 1. D to E, we have 4. D to C, we have 1. A to C, we have 25. A to F, we have 10. A to E, we have 3. Okay, and that's it. So this is the graph. Okay, so once you note it down, our source is given that source is A. So we need to identify the path from A to B, minimum path from A to D, A to C, A to E, and A to F. That's our target. We need to identify minimum path for A to A, which is 0, obviously. From A to B, we don't know yet. So let's write it down as infinite. Infinite, not like this. A to B, A to A is 0. We know that. A to B is infinite. A to C is infinite initially. A to D is infinite. A to E is infinite. A to F is also infinite. Okay, initially it's infinite. Initially it goes like this. Okay. Then in the next iteration, what we will do, we will say that, okay, pick the minimum edge. Pick the minimum edge. It sounds like similar to Prim's algorithm. Okay, it sounds like similar to Prim's algorithm. Right now we have only A. Only A. Okay. So we will say that from A, which is the minimum edge? From A to A, we have 0. From A to B, A to C, A to D, A to E, A to F, which is the minimum one. If you have noted down this one, I will go back sometimes here. If you have this diagram on your notebook, you can check this one and check the reference that from A to B we have 50 directly. From A to C we have 25. From A to F we have 10. From A to E we have 3. From A to D we have 2. So 2 is the minimum one. Okay, so we can write in the next iteration, we can write it like 0. And we have reached to this 0 using A, infinite. Okay, just infinite is there. From it's infinite. We have reached to D with cost 2 via A. Okay. So we need to write two things here. That if we are reaching to a node from A, via which node? Via A we are reaching, okay? We are reaching to E with infinite, that's it. Now, you need to pick from A to B by either direct B or D. Okay, the next minimum you will pick. What is the next minimum? If we go, we can go via D or directly we can go via A. We can go via D. Okay, from A we have to reach either B, C, E or F. Either via D or directly from A. Because we have explored D and A only. Okay, so which is the minimum one? 25, 50, 3 and 10 here. If we go via D, we have 2 and 3, 5. We can reach to B via D with 5. We can reach to E via D as you can see here, it's 6. To F with 3. You can reach to F via D with 3. Okay. So you can see here that we are reaching to E with 3 and we are reaching to F with 3. Okay. So let's write it down. Now, okay, so this algorithm will take time and we will cover this algorithm in the next lecture. So you can assume that, okay, we will go to B, C, E and F via D or directly via A, whichever is minimum, okay. So we will see that instead of infinite, we will try to write it the exact number. So actually this lecture is lengthy now and we will try to cover this because it will take time, at least half an hour to make you understand this algorithm. It's very simple once we cover this. So instead of infinite, what we will try to do here that we will say that, okay, via A, whatever we can cover. Via A, let's see which all we can cover. Via A, we can go to B with 50, to C with 25, to D with 2, and to E with 3. Okay, and to F with 10. So this is all via A right now. Out of this, which one is minimum? This one is minimum. Okay. So using D, we will try to cover, we will try to reduce this cost. We will try to reduce all the cost using D. If we can reduce it, we will replace that. Okay, right now, A and D is sorted. Okay. So this whole thing is sorted now. And we know that A to D, we finalize that A to D will take 2. Now via D, can we reduce these costs? Can we reduce? If we can reduce, let's reduce it. Via D, can we reduce? From D, let's see that we can go to E with the weight 6. It's already 3. So it cannot go below 3. Okay. We can reach to F with 3 cost only. F with 3. So right now we are reaching to F with 10. Instead of 10, we will reach to F with 3 via D. Okay. And E is same. This is already sorted. C, like how much cost C will take? 3 only. Okay. It will also take 3. C will take 3. Via D, we are reaching to C. D, it will be 5. D will be 5. And it's already 0. So this is also sorted. Okay, 0. It cannot go below 0. So A to A is 0. A to D is 2. And it's D now. Now which one is minimum? We can pick this one, or this one. Okay, so let's pick this one. Let's cross this and finalize its distance. A to E is equal to 3. We know that. Now we can use this fact and this fact and try to reduce these costs. This one, and this one. Okay, this is how we can iterate it. So I will take a few examples, 1, 2, 3 examples and try to explain this in next lecture. Thank you all for joining, and I will see you in next lecture. And I will try to explain Dijkstra algorithm and some more graph related algorithm in the next lecture. Thank you.